Welcome to Xcentric Mold Engineering's webinar. If you are here for the Parts Troubleshooting Clinic, you're in the right place. I'm Connie, and I'll be your host for this session. A few things to cover before I turn over the webinar to our keynote speakers. This presentation is expected to last approximately 30 minutes. Q&A is included during the presentation, so feel free to submit your questions using the chat function located in the lower left right of the control panel. If we run out of time, all the questions will be answered. We'll follow up by sending you an email containing those answers, as well as a link to the recorded version of this webinar for future reference. With that, I'll now turn over the webinar to our keynote speakers, John Sidorowitz and Glenn Miller. John and Glenn, please tell us a little bit about yourself.
Thank you, Connie. My name is John Sidorowitz. I'm Vice President of Inside Sales and Customer Service here at Xcentric Mold. Been with the company almost 8 years now. Been in injection molding 15 years. Glenn, how about you?
Glenn Miller. I'm the tooling engineer here at Xcentric Mold. I have about 20 to 25 years of injection molding design and build experience. Looking forward to reviewing all these tools with you.
So how it's going to work, this is kind of our second time doing this, and then thanks to some previous visitors' feedback, hopefully we're going to make it better this time around. Kind of go through a part, describe its use, how it functions, any challenges that we had with the part, either on our side or customer design, point out significant features, and then during the time we're reviewing, feel free to submit questions. We'll answer questions after we review the part, give you some time to do that, and then repeat with some other parts with whatever time we have allotted. So this is a valve part. It looks pretty simple at first glance. Key features on this part are these small pass-through holes. Measure. Trouble with these holes being so small is cutting them in the tool, and actually let me bring up the tool so we can see actually how they're made and kind of go from there. So as you can see, this part has a few actions. These loose pieces here come out, and then this is the piece kind of in question that shuts it off on this surface, creating those through holes in there. When you're dealing with grills or a lot of through holes, venting, anything like that, always try to get as much draft as you can, or add as much trunk to the bottom of it as you can. To strengthen that for during the mold process, so you don't get damage, bending, things like that.
And any time you could get a radius down in the bottom of that, a lot of times that's not possible, but anytime we can get a break on that corner, that strengthens the part, and that just helps out the overall performance. You can see the two mating inserts there. Obviously we have a piloted lock to assure that those two are aligned properly during the molding process and they don't shift during injection pressure.
That's really the key feature to this part. And again, just adding draft to these type of features, not going zero draft or straight wall, just helps with demolding and with the part.
Okay, we are going to move on to our second part here.
All right. We have what we call a Y body for any medical customers that we have on with us today. You'll probably recognize this. These are typically pretty challenging parts. Let me change this. Just because of the creative or the shut off. So if we do a section view here, you can see on the inside of this part, just the unique shut offs that we have from this component coming in, shutting off on this pin, and then these small areas within the part, and then a thick section. So what I'm going to do is bring up the kind of the tooling and how we kind of configured it and how the shutoffs look. So you can see from here, we've got 3 pins coming in, creating the 3 legs of this Y body. In addition to that, we have 2 pins coming in from the core and cavity. Their function is to stabilize. If I shut this part off, you can see that these 2 pins stabilize this, holding it center in the tool, and this component actually is drawn in and locks in this section, keeping everything straight within the tool during ejection.
No, I mean, really the key is to make sure all the pins don't move during injection. The pressure will sometimes make the pins flex. These locking features assure that we get consistent wall stock and a concentric uniform diameter on inside and outside of the part.
And that's, yeah, really the challenge is keeping everything straight, centered, with good clean shutoffs, minimizing flash.
As you can imagine, on that angled pin, as it shuts off on that core pin to the right, that's got to be pretty much spot on and perfect as a shutoff. Otherwise, you're going to get some internal flash and issues, and a lot of times that's unacceptable from the customer because of the function of the part. So that's something you definitely got to. It's not as simple as it looks. That shutoff there is key.
Right. All right, we've got a few questions coming in already. If you've got more, just feel free to add them. Let's start with, what is the size of the small pins? I'm assuming we're referring to these. 1.17 millimeter on those. So do the transverse pins withdraw prior to injection? With this tool, this was actually a prototype tool, so everything was manual, hand loads. So the part would be ejected with all these pins into it. The only pins that would be in place are the 2 smaller ones. Those are housed in the core and cavity. There's more components to these, but they would all be pulled from the part after injection.
And that's due to this. This is actual prototype tooling, quick turnaround. If this was a standard production mold, then yes, there would be some action on these, and they would open up as the tool opened to clear the holes before the part is ejected.
Okay, and it looks like we had a question on the first part, kind of maybe leaning towards the same question. On the first part, are the side pulls hydraulic or mechanical slides? If mechanical, how do you keep the small hole cores from being damaged from the mechanical slides as the tool locks? On that tool, the way it was, we can pull it back up, but the part of the tool that created those small through holes was actually in the cavity of the part, I believe.
Basically, the same assessment is with this tool that's on the screen. It all is a hand-loaded mechanism, so the part comes out with the hand loads intact, and then it's demolded off of all the hand loads. So I understand the question, but with hand loads and it being a manual tool, there's no issues with collision or damage as it's being removed.
Right.
Well, John gets the next part loaded up. We've seen some questions with regard to webinars. You can access our webinars at any point in time if you go out to the website at www.xcentricmold.com. You click on the webinar section. You will see webinars just like this and others posted. As we finish them, you can access them at any point in time out there. So thank you for the question with regard to webinars.
All right, for our third part, it's a closure cap. At first glance, pretty straightforward. We do have a arrow indicator on the side there that is not in the line of draw. That required an action. The interesting part is when we kind of go on the inside of this part, we've got some multiple undercuts, strippable undercuts, referring to these, and then we've got some kind of overhangs that you wouldn't be able to strip out from the mold. Just too large, too deep. So the challenge was, how do we make this part? And it ended up being multiple actions. We'll just do a section view so we can kind of see what was going on inside the part. I don't know if it's really going to show us. Yeah, got some bad data here. So here's essentially the portion of the mold that makes this part. So we have this loose piece here that creates the arrow indicator on the side that we looked at first. Then in order to create the features on the inside, it's almost like a puzzle. Let me just remove that out of the way. So this part, this area of the tool would be stationary in the core and would eject out from the part. Stay with the tool, part would eject out with these two loose pieces still intact in the part. Operator would come out, pull this one back, move it out, pull in, remove it out, thus creating those internal undercuts.
John's pretty much explained exactly how that's done. The motions he showed is exactly how the operator at the press would demold this part, that center core piece staying with the tool as it pushes forward with the inserts, and just pull them away from the threads and undercuts, and the part is clear.
Okay, are there any questions with regard to this part? Okay, we do have a couple questions. Could the operator remove two pieces be automated, or did that have to be a manual process?
In a production environment, it could be automated.
Potentially, it could be automated with some sort of core,
collapsible core.
Or collapsible core. Obviously, much more intricate, much more
expensive,
detailed, and expensive tooling. What we show here in our prototype tooling is a much more efficient and cheaper version for creating that undercut and demolding part.
And yeah, just essentially proving out the design for the customer to see if it's something viable, moving forward at a low cost. The difference with the manual versus auto, manual tools, you have a lower tool cost, a higher piece price, and obviously the reverse when you go into automatic tooling, you'll have a higher tool cost, lower piece price. So really going to depend on your project and what your needs are and expectations. All right, so barb features are pretty common among plastic parts. Typically, or most customers at least, cannot have a parting line anywhere on the first barb, just due to whatever they're putting over it, silicone tubing, any way to reduce the risk of cutting open any tubing that's attached to it. Right. This part also has a couple undercuts, but this part is more focusing on the barbs. There is some intricate, shut off here, coming from this side to this side, tapered wall. So bring up the tooling and so we can kind of see how that was. Get rid of this really quick. So you can see essentially this is another loose piece, or hand load we call it, that basically encapsulates the end of each part on that first barb, moving the parting line from what normally would be along this edge to about here where the rad breaks.
As John said, the reason for that is that the customer, at least on that first bar, does not want a seam running along the entire edge of that bar.
And, so here we can kind of see the innards on how those unique shutoffs are made. Once again, having a lock, this pin into that to keep everything straight, centered during injection.
Okay, do we have any questions with regard to this part?
Looks like we got a couple. Let me expand this a little bit.
We do have a few.
Does building prototype molds with pick-out cores and having the anything it takes mentality do more harm in the industry than working through production issues up front? Sometimes designs get all locked in based on prototype methods and are impossible to make in production. Really good question. It can happen. We try to, do our best up front, due diligence with our customers. Even though it can be done in a manual environment, express that it may not work in the production environment.
The understanding is that, yes, if we have hand loads and removable inserts in a production environment, those could be core pulls, whether it be hydraulic or mechanical. Sometimes the prototype tooling is a way to prove out whether or not you can actually have a part shape that way, and might need some adjustments in the design phase before they go to production tooling. So it's kind of a test sometimes for the customer's part design as well.
Yeah, there's going to be some designs where you're not going to be able to fully automate ever. Just due to the fact that the way it needs to be designed or needs to be made.
Right, and we've had parts and tooling where we've gone through the design process, built the tool, went through a couple iterations of how we're inserting and demolding this part, and that simply will help us help the customer. Possible future design corrections, or possibly even certain part features could be a secondary operation that they can also implement if they're going to go into full production with full production tooling.
Then we have another question. Will there be an example of a microfluid device? Not today. Unfortunately, we've got, I think, one more part to go through, and it's overmold for electronics. But we can keep that in mind for next time.
Good question.
All right, so this part is an overmold. It'd be more insert molding, I guess, than overmolding. We're actually overmolding a thermistor. Sorry, can't say that. Let me do a... So as you can see, there's a couple wires that lead into this part with this sensor that gets overmolded into it. So the challenges we had with this one mainly is we're holding on to wires.
Aren't always the most rigid feature, and can move quite a bit.
Right. On top of that, we have nothing stabilizing this piece in the part. This was a risky part. The customer was well aware of the risks. Just with, filling this part, this thing could blow around, bend up, bend down, bend right, break. They could not have this open to any air or outside conditions, so they needed it encapsulated. So we went with it, and we were pretty successful with it. Because gating did come into play, and forcing material in and up to keep this from flowing down. And again, it's a thick part. This was a TPU material, or a TPE, so it was a rubber type material, and that was a challenge with this one. And kind of break down So here's the part, and this is kind of the breakdown of how the tool looked. Core side's down here. So the electrical component would be loaded into this piece here. Wiring would go through, and then be held in place, and then loaded into the tool and then the part. We have a dual gate, so the runner splits into here. Let me just hide this part so we can kind of see. Oops. How it flows into the part. Material flows in underneath and then up, keeping that thermistor in place.
Yeah, I mean, the key is the direction that we're feeding the plastic into this component to keep that insert in place and not flexing down to where it's going to break through the wall of the part.
Okay. Does anybody have any questions with regard to our final part for the day?
It looks like we've got one. Could you give some tooling and per part cost numbers of these parts? Unfortunately, I don't have those in front of me. And it's really going to depend on materials. I mean, every part's going to be different, so it's hard to put numbers on these. I mean, if you have a part that you need a quote on, even though it's not in its final stage, feel free to go through our website and submit it for quote. We'll get you a quote back within 24 hours, and get you some pricing to at least get you started or get a good idea of where your part's at.
We have an additional question here.
On the overmold,
more.
How did you close over the runner? Well, that's all captured in the core and cavity, which I'm not showing here because it's really just pockets that hold these pieces in place. So that's what's creating the runner system. Are these molds aluminum? Yes. We will insert out with steel where necessary if we have thin tool conditions, small features, anything like that. But main core cavities are QC10 aluminum, which is a high-grade aluminum.
There are instances where we built the entire tool and all the inserting with aluminum, and due to wear issues or, as John said, ability to maintain a very small detailed feature, just a few thousandths thick, sometimes we will upgrade, per se, the inserts to a P20 or a steel material if necessary.
We do offer a lifetime mold guarantee on all our molds, so it'll produce parts for the life of the project, whether it be repairs or we have to make a new mold.
Okay. Well, thank you for joining us today. We look forward to seeing you at other webinars here with us at Xcentric Mold. For any questions or interest in our products, please visit our website at www.xcentricmold.com. Our social channels, or contact us directly at 586-598-4636, or an email listed on your screen below is sales@xcentricmold.com. A recorded version of the webinar along with the answers to the questions will be sent within 24 hours. Thank you very much, and we hope you have a great day.